Hello. Just this? Okay. We can go ahead? Okay. Good evening. And this is the second public lecture of ASI here in Indore. On behalf of ASI, we are quite pleased to have Robert Kushner for today's public lecture. And also on behalf of ASI, we are quite thankful to him for agreeing to give this public lecture and attending ASI here from his busy schedule and taking detour from his travels in India. So Robert Kushner is now TMT International Observatory Executive Director, and he is also Clowness Professor of Harvard University. Robert Kushner did his graduation in Harvard College, and during that time, he got a Bowden Prize for literature. What literature is called useful and polite literature. I don't know what that means. Maybe I should look at that article. So after his graduation in astronomy in Harvard College, he moved to Caltech, and he did PhD in astronomy there. And after that, he moved to as a postdoc in Kitt Peak. Kitt Peak National Observatory. And later he moved to Michigan University. There he served more than 9 years, and there he rose to chairman of the Department of Astronomy there. After 9 years stint at Michigan University, he moved to Harvard as a professor. There he had almost like 31 years of innings, and then serving at various capacities, like chairman of the astronomy department and the head of the optics and infrared astronomy division there. So, and after that, he moved to Gordon Moore Foundation as a chief scientific officer there, and there he has overseen almost like $150 million every year as a philanthropic activities, mostly for the science and engineering activities. So recently, last year, he took an appointment as a TIO executive director, and today he's also going to talk about the TMT project. Dr. Kushner, not only as a eminent scientist and science administrator, so he made path-breaking discoveries, particularly in the supernova research field and their application to the measurement of the history of the universe. And he is the author of more than 400 scientific publications, and that garnered quite a lot of citations, which runs into more than 66,000 with the H index of close to 130, which is quite rare, having a H index of more than your own age. It's a very rare achievement in the scientific the field. And he's a member of the US National Academy of Sciences, the American Philosophical Society, and also the American Academy of Arts and Philosophy, and many other intellectual and academic societies. He has served as the president of the American Astronomical Society and received the James Craig Watson Medal of the National Academy for outstanding contributions to the science of astronomy, and the Gruber Cosmology Prize as well. He was awarded the Wolf Prize in physics for work that led to the discovery of cosmic acceleration, and Breakthrough Prize is shared with his two students, Brian Smith and Adam Rees, and then later both of them won Nobel Prize in 2011 for discovery of cosmic acceleration. Professor Kushner is also a popular science writer and speaker. His book, The Extravagant Universe, Exploding Stars, Dark Energy, and the Accelerating Cosmos is quite popular and has been translated into many different languages. And today he's going to speak to us about the 30-meter telescope and the world of science. Robert Kirshner.
Thank you, Eswar. And I just remind you that that H-index thing is very bad to use. You know, as a dean, you should know better. All right. I'm going to talk today about the history of science a little bit, the history of the universe in particular. So that's 14 billion years in about 40 minutes. To do that, I have to leave out a lot of people, mostly people who have written, other people who have written papers in the field. And so I'm going to start now by showing you a little bit about the history of discovering cosmic acceleration, something that Ofer Lahav alluded to this morning. And then I'm going to tell you a little bit about a new method using infrared observations of supernovae, observations in the rest frame infrared, that is very promising and should lead to even more reliable measurements of cosmic expansion and might help with the Hubble tension that we heard about this morning. And then I'll turn to the use of the big telescope for science, mostly a broad brush approach to tell you the range of science that the telescope, the TMT, will enable. But I'll also mention a little bit this supernova business. Okay, so that's the plan. Let's get going. So, you know, the idea here is to figure out what the world is made of. And I showed this slide a couple of days ago at a public talk. And afterwards, someone said, well, air, earth, fire, and water. But he told me that in the Indian tradition, there's also the vacuum, which struck me as exactly the right thing, because what I'm going to be talking about is the properties of the vacuum, the negative pressure of the vacuum, the cosmological constant. And so here is a shorthand picture of today, of the universe, not very quantitative, but kind of vivid, that we're talking about looking all the way back to the Big Bang, and to see the era of expansion and cooling for the universe. And then, interestingly, and Lahav pointed it out very in a good way, that we switch over from being dominated by the decelerating matter to the accelerating dark energy. And that only took place about 6 billion years ago. He emphasized that it was so recent. I don't know. Anyway, here we go. And then here we have the same idea, only with the coordinate system on there. I don't know why that is so helpful. But anyway, with this history of cosmic expansion is something we've learned about, and in a surprising way in the last 20 years. Now, I've already alluded to, and Ofer Lahav talked about the cosmological constant. Einstein, you know, put that into his equations to make a static universe. And he said that term is necessary only for the purpose of making possible a quasi-static distribution of matter as required by the fact of the small velocities of the stars. So he wasn't really wrong. The velocities of the stars, by which he meant stars, are relatively small. And it was only later that we discovered we live in a big galaxy, in a big universe, where the objects whose motions you should pay attention to are the galaxies. So Einstein justified lambda, but he soon found reasons to back away from it. And the change from thinking about a static universe to thinking about a dynamic one, an expanding one, came through observation. And the great telescope of its time was the 100-inch telescope at Mount Wilson. One thing I'm going to repeat more than once is that the discoveries that we make depend on the instruments that we build. And of course, we're heading toward building the 30-meter telescope. We hope to make great discoveries with that. I just want to emphasize the engineering of the sort of just after 1900 world. You can see this big iron thing with rivets on it and so on in a giant rotating dome. And the observer would sit on that little chair all night, and he's on that platform that would go up and down. It was quite dangerous. One person fell off and nearly was killed. Here's Edwin Hubble sitting on that chair, and you can see he's leaning back. I think he's showing off for the photographer. Now, Hubble, as you know, measured distances to galaxies, first from looking at Cepheids to show that Andromeda and a few of the other local group galaxies were not part of the Milky Way, but 20 times farther away than that. And then he devised a set of methods to estimate the distances to galaxies, mostly through the brightness of the galaxies themselves. The Cepheids he could only do very nearby. But here you see a linear plot on the horizontal axis distance, on the vertical axis velocity, and you can see that the points it's kind of noisy, but the points drift up. This is the velocity-distance relation. We call it Hubble's law. He called it figure 1. Okay. Now, the way we tell the story is that Einstein sort of said, okay, if the universe is expanding, then who needs the cosmological constant? But there was a little moment where the supernova, where the expansion of the universe was known, and the cosmological constant was around, where people thought, well, maybe the anti-gravity quality, the expansive property of space, the accelerating property of lambda, could be the cause for cosmic expansion. And here's a cartoon from a newspaper. It's in Dutch, but you know, English is a dialect of Frisian, which is a kind of Dutch language. Anyway, so you can read it pretty well. It says, what makes the ball blow up? You see it's somebody in the shape of the letter lambda. What makes the universe expand or swell up? It's got to be lambda. No other answer can be given. This was De Sitter talking to a newspaper and somebody turning it into a cartoon. De Sitter retreated from this position pretty quickly. I think he and Einstein got together and said, let's not talk about lambda anymore. And you know that when I was a graduate student, hardly anybody talked about lambda at all. We talked about trying to measure the history of cosmic expansion, and from that to infer the presence of matter, the density of matter, but we certainly weren't interested in lambda. That was the land of, sort of kooky cosmology. Okay, but Hubble also had another idea, and he said, kind of prophetically, this is in his book, which sold pretty well and I think was translated into several languages as well, The Realm of the Nebulae, supernovae can be detected at immense distances. And in principle, they are criterion of distance about as reliable as that of total luminosities of the nebulae. So here you see a supernova in a galaxy, that bright thing at the top. And then he said, actually, however, the maxima are so seldom observed and the supernovae themselves are so rare, they contribute very little to the present problem, which is the problem of expansion. So it's interesting. He understood that the supernovae potentially would be good standard candles, or at least luminous things that you could use. But the problem was technological, that you couldn't survey widely enough or fast enough to make this problem go forward. And that is a technological problem that did get solved. So just again, to show you a supernova in a galaxy, this is a Hubble Space Telescope image of a supernova that we observed shortly after HST was launched. Okay, and what was the technological breakthrough that changed this from being a potential thing, as Hubble thought of it back in the 30s, to being a real thing? And it was the technology advances that started with CCDs. So if you buy a digital camera, it'll have a camera in a detector in it that's at 10 megapixels or more. This is the state-of-the-art very expensive CCD that made my thesis advisor, Bev Oak, very happy, and it had 0.24 megapixels. But it was an electronic detector, the output was proportional to the input, and that meant you could do very good photometry of objects against a bright source, like a galaxy or the sky. Okay, and so skipping ahead, my graduate student Saurabh Jha made this plot. This is the last Hubble diagram I will show you that is linear. In fact, we never show them this way. That's linear in distance and linear in velocity. And what you can see is this is for type 1a supernovae, the kind that come from exploding white dwarfs. And we had a handful of them pretty well measured out to a distance of 600 megaparsecs, so something like 2 billion light years. And just for reference, Hubble's Hubble diagram would fit in that little red box down at the left. So Hubble was holding on just to the toenail of this story. And now with the supernovae being bright, as Hubble understood, we're able to measure larger distances. And we're able to find the supernovae because we had ways of getting more pixels on the sky. And we did this, this improvement kept going. I'll show you a little more about it, but there were two teams, as Ofer alluded to briefly this morning. There was the High Z team, which Adam Rees and Brian Schmidt and I were on. There was the Supernova Cosmology Project that Saul Perlmutter led. They're in red and we're in blue. The low redshift supernovae are almost all from our work with our colleagues at Cerro Tololo. And the high redshift ones, we had fewer but smaller scatter, and we were able to see what was going on. What's going on is that Hubble diagram, which is log-log, is curved. And you can see down in the bottom where I've taken out the 45-degree slope as a function of redshift, going from really nearby, redshift of 100th, 3,000 kilometers a second, to redshift of a 10th, out to redshift 1, that the nearby supernovae scatter about the horizontal line. That's the Hubble law in the region where the acceleration or deceleration is negligible. But then at higher redshift, the lines diverge. And Ofer Lahav this morning said, you know, when he was a graduate student, it was that bottom line, the one that's, let's see if I can do this without wrecking things. Yeah, it's that bottom line that we were all taught was what we should expect. A coasting universe would be something like this. An accelerating universe would be up. And you don't need, although we did use, the sophisticated tools of Bayesian inference to figure out what this was consistent with. Nevertheless, you can see that the points lie up, and that means that we live in a universe that is accelerating. Now, the going beyond the discovery of the phenomenon, of course, you want to do a lot better job. Ofer was also very good about asking, well, when do you stop? But that was 20 years ago. We knew we had to go forward 20 years ago. And here is part of the reason why it's possible to do better now. And this is a great big CCD array that John Tonry built for the Pan-STARRS telescope in Hawaii. And with that, you can look at a chunk of the sky, and you have a very good chance in the space of a night, if you can handle the data, to find the supernova. And so here's how that went. And we do that. So today's diagram for Hubble diagram for type 1a supernovae is shown here. This is the Pantheon Plus analysis. And they've done you the favor of putting out the model here. And you can see that the scatter about the model, which is an accelerating universe, is actually pretty, well, it's medium size, and it doesn't vary with distance, which means we have a pretty good grip, except for very nearby, where the peculiar motions dominate. But from a redshift of a few thousand up to redshift 1, the techniques for type 1a supernovae work pretty well. Now, those techniques include dealing with the shape of the light curve and dealing with the color of the supernova, and I'll show you in a few minutes a way to do better than this. But this is sort of the state of the art. And if you do the analysis in the way I alluded to, then you can make a measurement of the fraction of the universe that's in the form of matter, dark matter, as we know, and it's around 0.3. And the fraction of the universe that's in the form of the dark energy, that's what it is, which is around 0.6 and a little bit, so that there's no way anymore that a value of 0 is consistent with the data. So, you know, every once in a while you read an article in the newspaper that says, well, maybe this is just an error of analysis. I don't think so. Another thing to notice about this diagram is that it's a little hard to see here, but in the light blue are the uncertainty contours. These are like 1, 2, and 3 sigma contours for the parameters. The light blue ones that are smaller are only the statistical errors due to the size of the sample. The solid red stuff includes the systematic errors, and that's quite a bit bigger. That's an important point. That's the thing that Ofer should be thinking about when you stop burning the toast. And that is, we've moved from the era where the samples are too small to make it certain what the measurement is, to the situation where the calibration, the corrections for all these corrections for reddening and for intrinsic color and all that stuff is bigger than the statistical error. So that's telling you something about how to proceed. Focus on the systematic errors. And so I got to show you a little bit about that. Einstein was pretty surprised by the accelerating universe, and that was a big deal. This picture has become more or less a standard thing. It's really quite extraordinary, though. You should take a minute to think about it. Everything you have ever seen is made of atoms, and it's only a small fraction of the universe. It's also, if you're an academic administrator, if you were the dean, or you were the head of the Department of Science and Technology, this would tell you how to do things. For atoms, that would be chemistry, about 4% of the budget, I would say. The dark matter, well, let's call that physics, because we hope that they'll be able to measure it, give them 23%. And then the astronomers should get 73% of any reasonable science budget. Okay, so we're part of the 4%. Discovering something with a new instrument is a really important thing, and it changes the way you think. So here's Galileo with his little telescope out in front of the palace in Venice, and here's what he said. Oh, what did he say? He turned on. He said, "All truths are easy to understand once they are discovered. The point is to discover them." And as I say, the value of using instrumentation, advances in instrumentation, to discover things is highly valued in science, of course. So here we are in Stockholm. Okay, Brian Schmidt and Adam Rees are holding the medals, but we all got to stand on the stage there for a second after the king and everybody left. Okay, now I want to switch to the subject of getting better control of the systematic errors. How do you get better control of the systematic errors? And the answer is, it turns out, since some of the systematic errors come from extinction by dust, and some of it comes from our ability to correct for the light curve shape, which I'll show you in a second, there is something pretty obvious, which is if you work in the blue, so here's, B-band, and you see this blob of dirt in our galaxy. If you switch out into the infrared, so here's at 2 microns, your ability to see through is much better. And of course, that's something everybody knows, but this is kind of a vivid demonstration of it. How about the performance of the supernovae themselves, the intrinsic properties of the supernovae themselves? Well, we thought we would try to capitalize on this by doing a set of observations where we measured the supernovae in the rest frame infrared, both for the nearby and for the distant, cosmologically distant sample around redshift of 1/2. So this is a program that I led where we called it Infrared Observations of Supernovae 1A. And then if you scramble the letters around, I think that's called an anagram, you get raisin, and we thought that was funny. So we called this the raisin program. We used the ground-based discovery with those big CCD cameras like the one I showed you a minute ago. We used the pan-stars and then later the dark energy camera that Ofer was talking about. And when we discovered a supernova on the ground, then we went to the Space Telescope and got on the schedule, which is not easy, and got the observations as shown on the right. So there's the galaxy and there's the supernova. Now here's the thing that's a big bonus and that you wouldn't have guessed, or you might not have guessed, without building up a sample of nearby supernovae and studying them. And that is not just that the extinction is smaller, that you knew you were going to win, but here the advantage is that in the infrared, the supernovae really are standard candles. So I'll show you what this diagram is. Casey Mandel, who was my graduate student, and worked on this, and we've refined all this in the last decade. But here's the basic idea. For supernovae, in the optical, the supernova brightness is not quite the same. Here's the absolute magnitude. The supernova brightness is not absolutely the same. It is brighter for the slow declining supernovae. That's what this parameter is about. This is about how fast the light curve goes down. It is, you have to make corrections for reddening. So these points, these red points, are the ones which were done in the B band and then corrected to the black points that correspond to them. And you can see for some of them you have to make quite a big correction. If you were doing a cosmological study, you might want to throw those out because you weren't sure you were getting exactly the right correction for reddening. But in any case, you have a big correction for reddening, and you have to take into account the fact that the supernovae are not all exactly the same luminosity. The ones that decline slowly are dimmer than the ones that decline rapidly. Okay, now over here is a panel that's constructed from in the infrared with the measurements at the wavelengths that I was talking about. This is J, H, and K, so this is at H. And you can see something really interesting, that for supernovae that have different decline rates in the blue, so they have different luminosities in the blue, they have the same luminosity all across the board in the infrared. And you get the extra fact that the corrections for reddening are very small, so you probably haven't made a big error. This is nature's way of telling you what you should be doing. You should be making the observations in the infrared and making that whole, constructing that whole Hubble diagram at low redshift and at high redshift in the rest frame infrared. And that way you would get all these benefits. So that's what we have been doing in this raisin program. Let me just show you what some of these look like. We did the discovery and the optical photometry from pan-stars and from the dark energy camera. I don't know what happened to energy camera. Here's one to look at. Here's from pan-stars, this is the galaxy, and here's the supernova. You compare that to an image taken, say, a month before, and the galaxy, of course, you can subtract out. These are digital images, after all. And there's the optical signal that triggered the Space Telescope observations. Then when we got the Space Telescope's observations, here's the same galaxy now seen in that 1.25 micron filter on Space Telescope, and here's the supernova, and you do the subtraction, it's much easier. You get beautiful subtraction. You can measure the flux in the supernova really, really well. And I'll come back to this point about being able to get high spatial resolution when I talk about the TMT. Okay, and so this is just another one. Here's the supernova in the galaxy. Boy, that's hard to figure out when you just look at it. But when you do the difference imaging, pretty good. And for the HST, this is now at a little higher redshift, so we're at 1.6 microns. Then you see the supernova and the galaxy over here. When you subtract, there's nothing left but supernova. So measuring in the infrared, very good. And having high spatial resolution, really good. And so this just goes to show there are certain redshifts at which the bands of the space telescope match up with bands on the ground. So this shows at about a redshift of 1/2, you get a pretty good match over here between the Y band, that's about a little beyond 1 micron in the for the low redshift guys, out at 1.6 microns at a redshift of 1/2 with the space telescope. So this is the systematic complications, and I'll show you some way that we're working on to diminish that too. Okay, so what do these look like? Here's a supernova light curve where this is R, I, and Z in the rest frame. Not in the rest frame, as observed. And you can see that we found these supernovae before maximum light. We have plenty of points to measure the slope after maximum light. And then the delay is between when we were sure we had a supernova, then the space telescope has to put it in the schedule, send it up, go slew to it, and all that stuff, usually take most of a week. And here we are getting a few measurements out in the bands that correspond to J and H that help us with do this work. This is at redshift of 0.36, and we could do it pretty well at redshift of 1/2 as well. Okay, so as I mentioned, there's this sort of persnickety business of how the filters line up, the so-called K corrections for the supernovae. And if you could get away from that, you could really do this problem better. And Casey Mandel and his student, Stephen Thorpe, have done a very nice job on this, producing this interesting surface. Now, what is this? If you look at it from this side, it's the spectrum of the supernova at each age. So if you imagine here at maximum light is day 0, and the supernova takes about 20 days to rise to maximum. And then it's easy to observe it for 20 or 40 days afterwards. And so if you look at it with a slice, this way, it's the spectrum that you would see at a particular time. If you look at it the other way, a slice this way, it's the light curve that you would measure at different wavelengths. So it's all the information that you need to do this correction for redshift, where you've shifted the bands at which you're actually making the observations, and they correspond to the rest frame wavelengths that are in this data surface. So this is the right way to do it, and we're just beginning to exploit that in the analysis. Okay, so this is another diagram like the other one. But I just want to say this is not as good as the current state of the art for the optical stuff that I showed you before, where there are thousands of objects, and we're moving from the statistical uncertainties into the systematic ones. Here, I'm pretty confident that the systematic uncertainties are smaller, but we don't even see them because the statistical errors are pretty big. The sample that we were able to do in this laborious way was fairly small. Nevertheless, if you compare what we've got from the Raisin supernovae, that's this sort of modestly tan set of ellipses. This is more or less what I was showing you before as the state of the art. It's better. But out here is what we had back in 1998, which was enough to see that the universe was accelerating. And that's just gotten better as the sample got bigger. This is going to get better as the sample gets bigger until we run into systematic effects that we haven't accounted for properly. So I'm very optimistic that this is the way to go for the future. And if you plot a Hubble diagram here, we cheated and took out the middle because we only had supernovae at low redshift and at high redshift. But anyway, the other thing I wanted to point out again is that the scatter at high redshift is not a whole lot bigger than the scatter at low redshift. That means it's intrinsic to the supernovae, and there's still more to be squeezed out of it in some way that we don't fully understand. Okay, now what about the future? Oh, the future is going to be great. Just look at this, anti-gravity boots and everything. Okay. Well, who's trying to think about the future? Well, here's a kind of a wordy document. It's from the National Science Board, the group that is in charge of the U.S. National Science Foundation. And they say, for the U.S. to remain a global leader in innovation, America's researchers must have access to scientific facilities that will astonish the world. Tools that let them see further, faster, and deeper. And then down at the bottom it says, the U.S. must cooperate with other countries such that U.S. researchers can participate fully, help set the agenda, and share equitably in the results. Tools that let them see further, faster, and deeper. And then down at the bottom it says, the U.S. must cooperate with other countries such that... You know how embarrassing it is to hear your own voice? Terrible. Anyway, hey, stop it. Research infrastructure needs for 2030 and beyond will range from desktop microscopes to billion-dollar telescopes. And so I'm here to tell you about the billion-dollar telescopes they're recommending. That's the one I think we should build. This is the TMT, or rendering, of course, of the TMT. And it is a 30-meter diameter mirror. If you compare that to the current world standard, that's of 10 meters, that's a factor of 3 in diameter. But it turns out your effectiveness in some ways goes like d to the 4th, as I'll explain. Okay, as I'll explain right now. So here you can compare the 30-meter telescope, which is really built in the same way that the Keck telescope was built 20 years ago. So it's a set of hexagons, tightly nested, carefully supported, that make a single surface, a single optical surface that's phased up to be a single mirror, just with those little cracks. And as I was saying, it's easy to understand that you'd get if you make the telescope 3 times bigger, you'll get 3 times 3, 9 times the flux. But the other point is, if you're working at the diffraction limit, and we think we know how to do this through adaptive optics, if you're working at the diffraction limit for a telescope, the size of the image gets smaller in each dimension by a factor of 3. So it gets more concentrated by a factor of 9. In other words, the change in effectiveness or some kind of number of quality number and speed in some contexts is a factor of 81. So this telescope is going to be, roughly speaking, 2 orders of magnitude more powerful than today's big telescopes. And that's why we've put so much effort into doing it. Here's another way to kind of think about the growth of telescope sizes. This is the history of telescope shown as a log plot. So this is essentially Moore's law, you know, says that the number of circuits on a chip goes up exponentially and with a time scale of a couple of years. And so your computer is out of date in a couple of years. And Gordon Moore, who was one of the founders of Intel, gets to sell you a new one. That's good. Well, it was good for the Moore Foundation. Anyway, it was good for Gordon. And so here's Galileo's telescope. If you are in Florence and the lines are too long for the art museums, go to the Science Museum and you can see it. And then here are the telescopes that people built in the 1800s, coming up to this one, which I'm sure is the 100-inch. That's the 100-inch. that I showed you before. Here's the current state of the art, the Keck, VLT, Gemini, and so on, which were built in the 90s. And if you ask yourself, well, following this line, things double every 50 years or so, when should we see the TMT? Well, this was made in the somewhat optimistic days before time had elapsed. But if you project it out, it's about 2030 where you should see it, and that is the zone which we're aiming for now. So the time has come to build these giant telescopes. The difficulty is it's not inevitable. It doesn't happen just because there is this diagram. It happens because of hard work. It happens because of making the case for it, doing it, and it happens because of very substantial appropriations of money. And so in the US, every decade we have a decadal review. This one got slowed down a little by COVID, but the National Academy gets a bunch of learned people together, and we try to plot out what the future is going to be. It says, because of the powerful potential that large telescopes with diffraction-limited adaptive optics have for astronomy, and because of the readiness of the projects, we've been working on them for a while, the survey's priority for a frontier ground-based observatory is a significant US investment in the Giant Magellan Telescope and the 30-meter telescope projects, ideally as components of a coordinated US extremely large telescope program. Okay, so this is advice for the US. Fund the 30-meter telescopes. And we expect that they will. We're hoping that they'll do it for all the right reasons. It's essential for keeping the US community's global scientific leadership. Well, you heard that. And the scientific range of the telescope is really fantastic. It's not just to observe the infrared from distant supernovae better, but we're hoping we're going to do something on exoplanets, find Earth 2.0, something like the Earth, search for life on other planets through spectroscopy. There'll be physics, new messengers and new physics. That's a category for gravitational wave events and relics. This telescope, what we know about gravitational wave events is that they're faint and fleeting. And that means if you find one, you got to get over there pretty fast. And if you have a big telescope, you'll be able to follow it for a while and learn what these neutron star collisions really are doing. Black hole formation. And of course, the question of the dark matter and the dark energy are unsolved problems in physics, where astronomy is at the moment the only path to learning more about this mysterious stuff. That's 96% of the universe. We've heard a lot in the talks and in the posters. I saw this about the physics and chemistry of galaxies. These telescopes will let us look at the first galaxies. And they will also let us look at black holes, the very early neighborhood of black holes, and chemical evolution in the universe on a very long time scale. So these are all topics. I was here sitting in the session on stars, and these are topics that are part of what we're doing now and what we're going to be able to do with the 30-meter telescopes. So to say it in a most positive way, it's not just for astronomy. These telescopes will address deep questions of fundamental physics. They'll probe the geology, the density, and the atmospheres of exoplanets. It'll touch on the physical chemistry of ice and dust. And, we don't want to promise too much, but it could revolutionize biology. So nature is doing experiments on planets, or has done them, in ways that surely go beyond our imagination. And we have a lot to learn on that subject. So sharper tools lead to discoveries and eventually better understanding. I think this is a big advance, factor of 100 basically, in a kind of figure of merit that is well worth the effort. And so here's the story for life on other planets. It says, they just built a way more powerful telescope. everyone put on some pants. Okay, that's not really what's going to happen. Okay, so let me show you a little bit. There are some ways in which TMT is even better than JWST. JWST has been a fantastic step forward, but because the mirror is bigger, the diffraction limit is smaller, and we'll get images that are 4 times sharper than JWST. It's going to collect 20 times more light, so for faint things, that's really going to help. It'll have a bigger field of view, and here's something interesting. A space observatory is a fantastic thing, but you cannot go back there and renovate it with new instruments the way you can with a ground-based telescope. Well, they did that for the Hubble Space Telescope, but we're not going to do that again going out to the Lagrange points. So it's going to be state-of-the-art for 50 years during its lifetime. And it's a lot easier to build, fix, and improve. Okay, so this is supposed to show you, this is supposed to be ground-based resolution in a crowded star field. That's HST resolution in the same field. That's JWST resolution in the same field. And this is what you'll get with the adaptive optics at the diffraction limit for the 30-meter telescope. So you can just imagine how much better we'll be able to do if you want to look at the properties of the individual stars or anything looking at a dim object next to a bright object. There will be many, many applications where the resolution is really important. Here's one. How do you see the dark matter? Well, how do you learn something about the dark matter might be a better way to say it. But as Ofer mentioned this morning, of course, there's lensing. He was talking about weak lensing. This is strong lensing where due to the presence of a massive object in the middle of this ring, you can image the properties of you can lens the image of a distant galaxy into a ring. And of course, we've known about this for a while at radio and in optical. The point here is that if you can do this with sufficient resolution, you can tell whether the dark matter is smooth or clumpy. So on the left side is 8-meter resolution, and that little red box is where they want to direct your attention. Over on the right-hand side is a simulation of what you would get at the 30-meter scale, and it turns out this the narrow shape of the ring and so on helps you put a constraint on how lumpy the dark matter is. So you'll be able to learn things about the dark matter because of the high resolution of the telescope. Here's another case just for fun. Black holes and galactic centers. Well, our galactic center. This is about what you have with Keck and the current AO. With the 30-meter and AO, you'll do a whole lot better. Let's watch again. So the first instant is the ground-based resolution. This is what Andrea Getz and her group at UCLA have done with Keck. And here's what we can expect when we have the 30-meter telescope. You'll see more stars because they're fainter. You'll see them in closer to the black hole because the resolution's better. And you will go from just measuring the presence and the mass of the black hole to beginning to test general relativity on those scales. So it's a big change, and it will be a quantitative change that's going to be a qualitative change in what you can learn about the gravitational effects of black holes. And as you know, Andrea was the 4th woman ever to get the Nobel Prize in physics, and here she is, very happy to do it. She didn't get to go to Stockholm, though, because of the COVID, so sorry. Anyway, but here she is. Okay, what about this telescope? Well, it's an international partnership. You remember when I was reading this document that said how U.S. astronomers need to stay in the lead? It said big telescopes are going to be too expensive and too few to do it that way. We're going to have to cooperate with others, and we are doing that through the 30-meter telescope International Observatory. As I like to say, international is our middle name. And these little flags show you different parts of the telescope that are being built in various places. First of all, I didn't know where to put the software. The software is up here, and it has been done in India. The observatory software has been done in India. The primary mirror, this big thing down here, which has hexagons in it that I was describing before. There are going to be hexagons made in the US. We know how to do it because we did the Keck, we did the JWST, and at the very same factory, the A-team of the world, we're going to do the sum of the mirrors, but it's too big a job to do at just one place. Japan knows how to do it, and I'll show you that in India, people have learned how to do it, they've built a facility, and they're going to be able to make a very big contribution to the telescope. Okay, and there are other areas on instruments where India has also contributed and will contribute more. So it's an international telescope. India is really in it and doing a great job on the mirror system. Well, okay, here's the ambassador to the US shaking hands with the head of the National Science Foundation. And they had a smiling handshake a little while ago. I want to make sure that the next time they do this, that in that folder, one of the things that's listed is TMT. Here is the second in command at the embassy, the deputy chief of mission, and she and I are standing there in the offices of the 30-meter telescope, so in Pasadena. So we've got the attention of the Indian Foreign Service, and all this stuff that you see on the table there are examples of other parts of the telescope that are being built in India. So the hexagons start out as what we call roundels. They start out as round discs. They are warped and polished to a sphere, and when you let them go, amazingly, they come to the right shape. That's what it says. And then we lop off the ears and make them hexagons. And people from India have been at that factory in California learning to do this for a year, and they're going to do it here in India. And where are they going to do it? It's at this India TMT optical fabrication facility. It's on the Crest campus, not too far from Bangalore. And it's a beautiful building. We were there the other day, and they've built a great long clean room where they're going to put in the machinery for the polishing. And they're going to do the hexing and many other steps in the construction of the mirrors. And here we are. I'm here listening to one of the people from the TMT India, and they're describing the instruments that they're building, the parts of the telescope that they're building right now. And they're going to do a lot more very soon because they have bought a whole set of the equipment that's of the kind that was being used in California. It's on the way to India now. It's going to arrive and be installed in that beautiful building. I can tell you that building is better than the building in California where the Keck mirrors and so on were done. People learned what they really wanted and incorporated it into the building there outside of Bangalore. Okay, so this is going to be the greatest advance in telescopes since Galileo. It's going to be a big jump forward. It's going to be a jump over JWST in some ways too. And the idea is that you'll go from the kind of imaging, so this is a simulation, but it shows you that when you're doing 10 times better than the space telescope, you're really doing something great. So, I just wanted to emphasize, we're doing this in the context of 2 observatories, one in the north, that's us, and the GMT, the Giant Magellan Telescope, in the south. I have that little epigram there. That's from Caltech president Tom Rosenbaum. He went up to Palomar, where the 200-inch is. And they had a little feedback. They had an evening of observing. And he said, being there was a powerful reminder of the scientific payoffs that can come from the combination of persistence and ingenuity built on the foundation of engineering prowess. And that's what we're going to do for TMT. We're going to be persistent and ingenious, and we're going to build these telescopes. Thank you very much.
Thank you, Bob. It was a wonderful and inspiring public lecture, and inspiring to build better facilities for astronomy. You can take some comments.
Sure.
Comments?
A little hard to see out there, so maybe if you stand up, that would help us know where to send the microphone. Yeah.
Hello?
Yes.
Yeah, hi. It's very nice talk. I have a question regarding what is the diffraction limit, up to which limit we can go using the TMT?
What's the diffraction limit?
Yeah.
Yeah, at 1 micron, I don't know the number. Do you know the number? At 1 micron, it's 30 milliarc seconds?
4 milliarc seconds.
Yeah,
4.
yeah.
Okay.
You know, you take 200,000 and divide by 30.
Yeah, at 1 micron.
Stunned silence.
Hi.
Hello.
I would just like to ask, when do we know where exactly have we proceeded beyond, we are still working with the locals at Hawaii, or?
Yeah, that's exactly the right question to ask. Send me an email, would you? No, that's exactly the right question to ask. The site, I think the technical problems and even the financial problems are, within our own control pretty well. But as many of you know, even though we had all the legal permission from all the permits and everything required, when we went up the mountain in 2014, there were protests. And the second time we did it in 2019, we showed that we hadn't learned. We were stopped by protests again. So it seems to me the place we have to put our energy is in working with the local community, because we can't get, just because we have the legal permission does not mean we're going to be able to do it. Mauna Kea is the best site. It's really where we should do it. And so we're working very hard with the local community. Our project manager, Feng Chuan Yu, moved to Hilo. We've hired people in Hawaii who spend all day on outreach, like the kind we've heard, so that's a contribution to the community, but also other kinds of help. It turns out that the Native Hawaiian community, quite properly, has been, well, not quite, they feel, and they are correct, that they've been treated very badly. And they're within the population of Hawaii, they have poor health care, they have poor education, they have poor employment prospects, and problems with housing. And all of these are broken promises, really. But they're not exactly the promises we made, so we're stuck in a bit with a social situation that we didn't construct, but where we better address the protests. So we've been working every day on meeting with people that, as we like to think of it, were our former opponents, and listening to what they have to say. They have a lot to say. It's a talking culture in Hawaii, and they have a long list of grievances. But after you listen for a while, which could be 2, 4, or 6 hours, depending on the site, then you can really talk about what would be the benefits and what the TIO as a member of the community could contribute. So that's what we're working on now. That's not quite an answer to your question of when will we know. I think that we've made a lot of progress.
Simultaneously, work is also going on and working towards, if it had to be moved towards La Palma.
Yeah, I'll tell you about La Palma too.
Do we have,
I'll tell you about La Palma.
Do we have a date as to when you think you can decide which site?
Well, we're going to have to tell the NSF by the end of the final design review. Maybe I should say that. The NSF came and did the preliminary design review. They've put us in the major construction queue. They're doing all the things that they need to do to move forward. But they move slowly. And so it could be 2 years or maybe a little longer before we get to a decision point. We certainly will have to tell them in our final, at the time of the final design review, what our actual plan is. Plan B is La Palma in the Canary Islands. We also have the permits there, all except one little thing. There's a lot of interest in Spain in doing it. The problem is, of course, it's, we have to get this thing funded in the US. So being in the United States of America, I think, would be very attractive to our congressional delegations. So we'll see how that works out. But to answer your question about the timing, we won't know before a couple of years.
Yeah, thanks for that excellent review. I was wondering, what are your thoughts on the relationship between the TMT and the other 30-meter class projects, particularly given the delay in the TMT project?
Yeah, we're working together. We're working together with the NSF and the national observatories to get the whole package funded and approved. So that's the plan. We have made a lot of progress with our friends at the NSF in convincing them that instead of having a showdown and choosing one, that a much better plan is to do both. And I hope they have the courage to do it.
Hello, sir. Thanks for your talk. I had a question on one of the instruments. So is there any plan to install polarimetric instrumentation in the telescope? So recently we had, until last year, we had SOFIA Hawk Plus polarimeter. So since the SOFIA facilities shut down, is there any plan to install any polarimeter in the 30-meter telescope?
Well, our initial plans include an infrared imager and spectrometer that will be behind the adaptive optics. There'll be a wide field optical spectrograph. People here are working on it a bit. A great big multi-object spectrograph that will work in the natural seeing, which is also very good in Hawaii. And we're going to build a high resolution spectrograph that works behind the adaptive optics. Their next generation could include other kinds of instruments, including longer wavelength infrared if we wanted to do that. I don't know the whole story on the polarization. I don't think so.
Yeah, we don't have plans for that. I mean, there was survey because of the year.
Use the microphone so we can hear you.
Anupama, you can say something else. She was looking at case study for the polarity.
Yeah, so I think the potential is there, but at the moment, I don't think we have a plan to do it. Is that right?
No, I don't think we have, but we did do a study on what could be the instrument polarization.
Oh, the instrumental, the intrinsic polarization. Of the
Yeah,
instrument,
the telescope, from the telescope itself.
Right.
And that study has been done so that, in case in the future, you want to do something.
Yeah.
But there was a proposal when they had the call for second generation from the time domain group, which included the instrument proposed by that included polarimeter.
Yeah. Well, I think
people are thinking about it, right?
Yeah. The telescope's going to take 10 years to build. We're going to have a first generation of instruments, and somewhere around the time when, as we get the telescope going, we'll want to be making important, real decisions about the second generation. And now is the time to start thinking about, what would be the pace of it and how we would do it. But let's not get ahead of ourselves. Let's get the telescope built and that first generation working.
Hi, sir. Talking about science on the telescope, like TMT is going to be like excellent for every single science case that you mentioned. Like it's great for exoplanet, it's for cosmology and for like gravitational wave searches. But at some point, like we should be asking this question: what should be the primary science case for TMT, and what should be the secondary like category of science cases? So, and your thoughts on like what should be like the primary science goal of the TMT and
yeah, it's a very good question. Send me an email. No, the idea is, of course, we should continue to think about this. For example, well, like the polarization, should you add a polarization capability to some of the other instruments? What would be the reason for doing that? What would be the, as you say, the case? I think the exoplanets are not just fashionable, but very, very rich. And JWST is going to do a lot and open up a big set of cases that are very interesting. But one of the natural advantages of TMT is that you can work in closer to the star because of the diffraction limit. And you can, because the instruments will work in the optical, you won't just see hot planets, you'll be able to see reflected light from planets. And that means you could conceivably see an Earth-like planet in the habitable zone, which would be, I think, a real step forward. So I would say the things I mentioned, that list is not infinitely long, and it will be a telescope that's capable of many things. And it's a little hard to predict the future, but I think the area of exoplanets is certainly growing. And as you heard from Ofer this morning, the question of cosmology, is we've done some fantastic things in the last 20 years, but is it going to be, as exciting 20 years ahead? It's a little hard to tell. But I think you have to be modest. You cannot predict very well what is going to be the most interesting thing that you discover. So, if the accelerating universe is the most interesting thing that the Keck telescope helped us do, or no, maybe it's the black hole in the center of the Milky Way. Well, anyway, there are things that you're sure you're going to be able to do, and then there are things that are just going to be surprises. And I think it's reasonable to expect that when you make this big a leap in the technology, and your sensitivity goes way up, your angular resolution goes way up, you're going to find new things. So, we should do our best to try to make the list of the things that are really important and that we will do. And I think the instruments that we're going forward with do reflect the science case for the telescope. But we shouldn't be too vain that we know what's going to be the hot topic 30 years from now. And I think we need to keep that discussion perking. That's why we have a science advisory group. You're all welcome to join in that activity. And there's some discussion of the current instruments, the science case, and what instruments we ought to do in the future. And that is the forum where we discuss that. And there's a website. Take a look. Okay.
So this comment you showed from Hubble about the...
I don't think your microphone is on.
So the comment from Hubble that you showed about the possible importance of supernova. But at that time, even nova versus supernova distinction was probably not known. So was it like more based on just the absolute luminosity assumed to be constant for these type of sources? Or
well, he knew that I think that's right. He was talking about novae because he didn't know that they were supernovae. That took Zwicky to convince him. But I think he saw that, roughly speaking, they were bright enough, and in the places where he had found them, they were roughly of comparable magnitude. So he didn't know that much about it, but I thought it was a very interesting remark, because it's the advance of the discovery part, the second paragraph, where he says, well, they may be good, but, we can't do it. That is the result of the increase in the size of digital detectors, where we, take these images and subtract one from another. So the way to do it before that was with photographic plates. You take, like on the Schmidt at Palomar. I did that. I found some supernovae using photographic plates and blinking them, but, this is a way to be sure that you can find a supernova on any night. So, for example, if a supernova is 1 in 100 years in a galaxy, that's 30,000 days. So if you look at 30,000 galaxies, there should be one that's a day old. And that's doable in a night on a medium-sized telescope.
Okay, since we are running out of time, and then these are the last 2 questions. 23rd.
Yeah. You talked about this local issue where you need to get permissions, etc.
Yeah.
Yeah. So I was wondering whether making a good plan, I'm from planetarium, so a good planetarium show, and making them come and see the free shows and talking to them about would that help quite a bit?
Oh,
and if you're doing that, then what's the kind of things happening?
Yes, the University of Hawaii at Hilo has a Imiloa Center, which is whose purpose is to combine astronomy and culture. And they have a planetarium, and they have a lot of activity there. Whenever an astronomer goes in there and looks around, they always say, oh, geez, there's so much of this cultural stuff. And when a local cultural practitioner goes in there, they always say, well, why is there so much science in here? Anyway, so that shows they're doing something right. I think it's a very good institution. But we need to do much more than that. The rural community is very poor, and they don't have the money to even for travel or going into this facility. So we have to work to help get them in there. When I was at the Moore Foundation, we helped a little with that. And also, we just have to do the real outreach and have the nighttime observing in the communities where people are. What they often say is, astronomers have been using our mountain for 50 years, and, we never see them, and they haven't helped us. And so we want to change that and build a relationship based on respect and trust. We have some ground to make up from the errors of the past.
Okay, one last question. Really, we're running out. Need us.
Yeah. Hi. You showed Moore's law for the aperture of telescope.
Yeah.
I want to ask if it is primarily driven by the engineering challenge to build larger and larger aperture, or the complexity of instruments that is needed to support them also plays a role in it. What do you think is the driving force in that?
Well, there have been some changes, but I think the engineering demand is to make the mirror lighter. Because if you don't do that, it'll warp under the gravity forces. And the surface loading of the TMT is pretty low. The thickness of the hexagons is like that. And they're 1.5 meters. And they're supported to a fraction of a wavelength. And across the gap between the mirrors, this is the very clever thing about these, the edge sensors allow, and the support structure allow you to keep things in phase all the way across that 30-meter aperture. So I would say it's a combination of 2 clever things. One is being able to make the mirrors thinner, and being able to do active support of the mirror shape. So that's a big difference from, building big lenses, which was the problem in the 1800s. So there are several technological changes, from refractors to reflectors and now to very lightweight mirrors. So it's an interesting question, and I think a historian of technology might like to really dig in.
Thank you. Thank you very much.
Okay, thank you. I've enjoyed coming to India, and it's been a real pleasure.
Now I request President of the ASI to give a memento as an appreciation from the ASI.
Oh, thank you. Oh, my goodness. Oh, this is so nice. Everywhere I go, people give me flowers. Thank you very much. I really appreciate it. And I've just had a really good time, and I got to talk to some powerful people and help them see how important the TMT is. Thank you very much. And I got to talk to you, which is even more important because you're the people who are going to get to use this telescope. Thank you. All right. Oh, very nice.
Okay, there is an announcement from LOC. The buses are outside, just where we have taken the photograph in the morning. And please try to get on the same bus if you remember the number. Otherwise, there will be volunteers staying outside if you can recognize them. And that would help us actually. So, see you all around. And whoever are staying in the campus, we have arranged a night sky observation in the ground, cricket ground, which is next to the Abhinandan building. And if you are interested, please join us to watch the night sky. Here in the IIT Indore, the